Hi, as you watch this portion of the video today, please make sure that you're taking really good notes. You've got a lot of diagrams, so make sure that as necessary you're annotating the diagrams, giving them a nice descriptive captions, adding detail as necessary, and make sure that you are jotting down any questions that you're going to ask me about. As always, do a good job on the questions, and when you get to the end, make sure you click all the way to the end on the survey. If you recall, one of the biggest obstacles to people widely accepting Wegener's idea of continental drift was that he didn't have a mechanism. He had lots of evidence, but not a mechanism for how such a crazy thing could have happened. That came a little while after his death in the form of paleomagnetism. Paleomagnetism provided not only additional evidence, but also a mechanism. So let's back up and discuss what paleomagnetism is. In your notes, there might have been a typo in the version you got, so make sure that it's paleomagnetism. Paleomagnetism is just a record of a record of magnetism in the rock. As the rock cools, it can record where the magnetic pole of the Earth was. Let's back up a minute. Hopefully you're familiar with the idea that the Earth has a magnetic field. That magnetic field is detectable when we use a compass. It's not exactly the same thing as due north, but it's pretty darn close, so when we use a compass, we can find where north is. That the magnetic pole attracts to the magnet in the compass. We can see that from rocks formed in the past by looking at the magnetite in the rock. Recall that magnetite is a mineral that's magnetic. However, at really hot temperatures, when the mineral is completely molten, it's not magnetic. So we can only see the magnetic effect of magnetite in rock when it's cooling. When the magma is cooling, the magnetism of magnetite aligns parallel to each other, as you see in this right picture. And so during the time that it's cooling, not after when it's fully cooled, not when it's completely lava, but the time when it's cooling, so in other words, the time the rock was formed, we can tell the direction of magnetic north. Magnetic north hasn't always been in the same place that it is now. So by looking at the records of the rocks that formed with magnetite in it, we can see a history of where it's been in the past, when that particular rock was cooling. One of the bits of evidence comes from the idea of polar wandering. So I mentioned that magnetic north hasn't always been in the same place that it's now. Right now, it's pretty close to the axis of our rotation. Not exact, but pretty close. In the past, by studying paleomagnetism, we've seen a number of things. Number one, we've seen that the direction of magnetic north hasn't always even been north. We've seen that it's been south. 500 million years ago, a little while after the Cambrian explosion, it was near Hawaii. We also see that the hemispheres didn't change in exactly the same way. Now that's a little bit worded there. If we look at the magnetite recorded in the hemispheres, the picture on the right shows where we have the different magnetic north pointing, where we can see that magnetic north was. Picture on the right shows what happens if we imagine that the continents were closer together, overlapping. When we superimpose, or in other words, back up where Pangaea would be, we see that the hemispheres did in fact seem to change quite a bit together if we take into account Pangaea. Let's pause for a second and review. I mentioned that the mechanism that Wegener lacked came from studying paleomagnetism, and that came from studying the sea floor. So during World War II, the sonar technology was used during submarine warfare. Afterwards, that existing sonar technology, scientists turned that, instead of being for war, turned it for studying the ocean. There were a number of important discoveries when we studied the ocean using sonar technology. One of which is that there was this whole system of land on the bottom. It wasn't just this flat ocean. It just didn't get deeper and deeper and deeper like a pond or a puddle. Instead, what we see, there's a whole system of trenches and a ridge. So a ridge is a spot in the ocean floor that rises with a little bit of a deep middle valley. A trench, on the other hand, is a deep, deep area where the deepest parts are the ocean. Additionally, when they studied the age of the seafloor, they found out that most of the Atlantic Ocean was younger than 180 million years old. If you remember your geologic history, 180 million years was smack dab in the middle of the Paleozoic era, right around the time we thought Pangaea broke up. So if you imagine, smack dab in the middle of the Paleozoic era, which was right around the time we thought Pangaea broke up. Okay, so enter the picture Harry Hess, who proposed seafloor spreading in 1952. Seafloor spreading explained the observations observed with the sonar technology. So in the 1940s and 50s, after the war, scientists, when they were studying and found all these ridges and trenches, they found one particular ridge that we call the Mid-Atlantic Ridge that runs straight down the middle of the ocean. That ridge, if you notice, not only does it go straight down the middle of the Atlantic Ocean, but the curves seem to mirror the coastlines, mostly. The ridge in the middle, that ocean ridge, was basically, again, the raised crack of the deep valley in the middle. Seafloor spreading is the idea that that's where new ocean is being created. So magma is rising up, coming out of a volcano, and cooling. That ridge is the volcano, and it goes the entire length of the boundary. That's where the newest rock is being formed. That then cools to become the sea floor. As more magma rises up, it pushes the recently cooled lava outward, and then the newest rock is right there again at the middle of the Atlantic Ridge. Meanwhile, on the other end of the plate, in the side of the crust that is far away from the Mid-Atlantic Ridge, what we see is that we see a deep, deep trench. So Hess's idea was that the deep sea trenches are areas where the crust is being subducted, or in other words, pushed underneath that. And so that trench, the deepest part of the ocean, represents where one crust is subducting or going underneath the other one. That's because as magma cools, it gets denser and denser and denser, and so the oldest crust would be the densest material, and it would go underneath them as the two come together. We call that slab pull. It pulls the plate down. It's almost as if you were trying to do that old trick where you pull the tablecloth out from underneath the plates, and everything stays put. I don't know if you've seen that. You might be too young for that. But if you do that and you don't do it right, and you pull the tablecloth, all the plates come with it. And that's the idea, that as the one plate subducts, the rest of the land comes with it. So you've got a push from one side and a pull from the other. Okay. And again, this is the side on the opposite side of the ocean, or sometimes on the opposite side of the plate. Okay. So when we combine these, once again, rising magma at the rift pushes the rocks apart, pushes the crust apart, and at the trench, sinking deep, dense crust pulls down the rest of the plate. So now Harry Hess was beginning to have a mechanism for plate tectonics that Wagner didn't. So what causes this rising of magma at the ridge? Well, the answer lies in convection, something you're hopefully familiar with already. So convection is the idea that material that can flow, like liquids, gases, and the mantle, which is a semi-solid, material that can flow is at different densities at different temperatures. Hotter stuff is less dense, cooler stuff is more dense, and so what happens is, because gravity pulls on denser material more than it pulls on less dense material, gravity pulls the denser stuff downwards. That displaces the hotter stuff near the core, and that pushes the less dense material upwards, where it can lose energy and once again get cold. We see that, you're probably familiar with it in a pot, when you see the water boil through a pot. In the Earth, the temperature differences we see are at the core and the surface. At the core, which is the hottest material due to the force of gravity and the friction and the interaction of the material, is hot at the bottom of the mantle. At the top of the mantle, it's coolest because the crust is losing energy to the surface. So we see our hottest material, which is least dense, down here. The most dense material is the cool subducting area, the part that's sinking down below. So this, as it's dense, gets pulled downwards. This material that's already less dense gets pushed upwards, creating this current. And at the ridge, that's why the magma is rising. Part of the mantle that can flow like this is called the asthenosphere. It's nearest the cold. Close to the crust, it's so cool that it's hardened completely. So when the denser magma sinks, the hotter magma gets pushed upwards. When the rising magma reaches the lithosphere, it pushes outwards and spreads out and cools, which is what pushes the entire plate. That creates a circular flow of magma rising at the ridge and sinking at the rift. The ocean floor is young because it's constantly being renewed as new magma rises from the ridge. You should have a diagram like this in your notes. Take a moment and make sure that you really understand it, and a really good idea would be for you to annotate it and add some captions and labels to it. Once you're done with that, let's pause for a moment and do a little bit of review. So convection is a great explanation for how plate tectonics can occur. But what's the evidence that convection is actually happening? We see that we have magma at the ridge, but how do we know that this whole convection flow in the mantle is occurring? Well, we come back to paleomagnetism, or magnetic pole reversal. Remember, I said that the poles haven't always been in the place that they are now. So Earth's magnetic field reverses polarity over hundreds and thousands of years. Magnetic north and magnetic south actually switched. That's why back in the day, at one point, magnetic north was near Hawaii because it was in the process of switching. Right now, as I mentioned, is what we call normal polarity, and magnetic north is near the North Pole. Okay. When magnetic north is near the South Pole, the compasses would point south, and we would call that reverse polarity. So how do we see that this is actually occurring? Well, we see this in our magnetite in our rock records. So that lava that's coming up from the rift, as it's cooling when it reaches the lithosphere, the hard part of our mantle, that's recording the magnetite, that's recording the direction of magnetic north. And so what we can see is that right now the magma that's rising up from the surface is aligning itself towards magnetic north. And if we go on either side of the ridge, what we see is that we see mirror image of magma that has been raised up, moving outward, and the recording of whether it's magnetic north or magnetic south is the same on both sides. The ages when we date the rock also matches, as does the polarity. And so as magma rises up, we see normal polarity, followed by reverse polarity, followed by normal polarity, and once again it's the same on both sides. You should graph something like this when you do your seafloor spreading lab. So how does this support seafloor spreading? Well, it shows that material on either side of the rift formed at the same time when polarity was in the same direction. Okay. And once again, as magma solidifies at the rift, it's magnetized because of the polarity, and that's recorded as it moves outward. And it would have looked something like this, where each colored band represents a different polarity. So the green section on either side, for example, would be the same age as the green section on the other side. And as the rock ages, it gets pushed outwards and outwards towards the edge at the other end where there would be a trench. In science, the more data we have to support our conclusions, the more confident we are that those conclusions are accurate. And with seafloor spreading, of course, we've got additional data. So one thing is seafloor drilling or ocean drilling. Ocean drilling has been able to actually age the rocks, and what we can see is that the oldest rocks are farthest from the rift, and the youngest rocks are closest to it. We can do this by ocean drilling as well as just by dating the fossils that we're finding in the ocean floor. We also see that the thickness of the crust increases with distance from the rift, which we would assume would be accurate if the sediment from the material in the oceans, as well as the fossils and the sea life that has died, settles down, and as you get older and older, we would get thicker and thicker. The ages they can record align to the polarity. Notice the plus being positive polarity or normal polarity and the negative being reverse polarity corresponds when we've actually dated and taken cores of the age of the rocks. This is true not only at the Mid-Atlantic Ridge, but this particular plate boundary is in the Pacific, near the plates near Mexico and South America. This ridge that we see here, as well as here, is exhibiting those same characteristics that we found at the Mid-Atlantic Ridge. Another phenomenon is found by island chains. Hawaii is a great example. It's called a hotspot. A hotspot is an area where magma is rising not because of a plate boundary. In Hawaii, it's just in the middle of a plate. And as magma rises, it forms eventually a volcano that leads up and eventually rises up over the ocean to make an island. What we can see is that as we age the islands of Hawaii, we can see that the oldest islands are the ones furthest away from the hotspot where there's active volcanism. And this chain of volcanoes shows that the seafloor has moved position. The hotspot stays in place, and the land over the top of it moves. So once again, the definition of a hotspot is a volcanic island or a seamount, one that hasn't risen up out of the ocean. And it exists in chains that vary in age, with the oldest being the farthest away from the hotspot.